In this video lesson, we're going to discuss hydrates, what they are, how to name and write them, and how to determine percent composition of a hydrate. Before we begin, let's go ahead and look at the general form of a hydrate, and therefore define what a hydrate actually is. If you'll notice in the form, the example that we're looking at is copper sulfate, then we have an asterisk with a 5H2O. The first thing to note that's important is that this is all one compound. This one compound is called a hydrate. Now, a hydrate consists of two things. The first part is the ionic compound. In this case, it's copper sulfate. Now, the ionic compound can change, but no matter what it is, a hydrate will always include an ionic compound. We call this specifically the anhydrous salt. Remember, salt means that it's an ionic compound. But let's look at the other part. When you see the prefix "an", what comes to mind? Well, when you think of "and", think anti, or without, or no, all of which are correct. When you see the term hydrous, what comes to mind? Water. So if we put the two together, anhydrous really means without water. Now, the asterisk does not mean multiply, but simply means attached. This is not just a regular ionic compound, there is something attached to it. And specifically, it's water. Now this part right here has an actual name to it. We don't just call it water, but we call it water of hydration. The reason we call it water of hydration and not just water is we want to be clear that this water part is in fact hydrating the ionic compound. All right, so we've learned that a hydrate is an ionic compound with a certain number of water molecules attached to it. In this example, there are 5 specific water molecules. Sometimes there might be 4, or 3, or 6, or 9. The number can change depending on how many water molecules are attached. Now that we know what a hydrate is and what it looks like, let's go ahead and figure out how we name the hydrates. Let's take a look at these two examples. We have NaCl star 7H2O and CuSO4 star 3H2O. First of all, notice by looking at them that they are hydrates. We know they're hydrates because of the asterisk that's in the middle. Remember, the asterisk means attached. Okay, let's go ahead and name them. The name consists of two parts. First, you have to name the ionic compound, and then you have to name the water part. The ionic compound is named just as it normally is. NaCl is named sodium chloride. If you have forgotten how to name ionic compounds, be sure to review that under the video lesson labeled Naming Ionic Compounds. Okay, sodium chloride has been named. Now we need to name the water part, the 7H2O. We need to indicate somewhere in the name that we have 7 waters. This is where Greek prefixes come into play. Do you remember the Greek prefix that indicates the number 7? The answer to that is hepta. Be sure to make sure that you remember all the Greek prefixes. Hepta means 7. To name the water part, we're simply going to call that hydrate, and we add that onto our Greek prefix. Therefore, the full name for this compound is sodium chloride heptahydrate. Let's take a look at the second one. First of all, we need to name the ionic compound part, CuSO4. Well, Cu is copper. But remember, copper is a transition metal, and therefore needs Roman numerals. We'll come back to that in a second. The SO4 part is sulfate. All right, let's figure out what the Roman numerals should be. You have copper matched with a sulfate. If we know that sulfate has a -2 charge, that must mean copper has a +2 charge to balance it out, and therefore the Roman numeral is 2 to indicate the charge. Now we've only done the ionic compound part. Let's go ahead and add the hydrate. There are 3 water molecules. The Greek prefix for 3 is tri. Therefore, the name of this compound is copper 2-sulfate trihydrate. Now what if we were to go the other way? Let's suppose I give you the name and ask you to write the formula. Go ahead and try these on your own, and then hit play to reveal the answer. For the first one, we have copper 2 chloride tetrahydrate. Copper is Cu, and chloride comes from chlorine, which is Cl. Now, before we move on, make sure that the charges balance. It is an ionic compound, and therefore, the charges must equal 0. The charge for chlorine is -1, but what about the charge for copper? It's transition. Remember, the Roman numeral will tell you what the charge is. Copper is +2. By doing the crisscross method, we would get that the proper formula for copper 2 chloride is CuCl2. That is the ionic part. We still need to add the hydrate. The asterisk indicates that it's attached. We see the Greek prefix tetra. Tetra means 4. Hydrate is the water, H2O. Let's look at the second one. Iron 2 oxide hexahydrate. All right, let's go ahead and name the ionic compound first. The iron 2 oxide. Iron is Fe, oxygen is O. Now let's look at our charges. Oxygen is -2, and we know iron is +2 from the Roman numeral. By having one of each, it looks like the charges already balance out to 0, and therefore no extra subscripts are necessary. FeO is the correct formula. Now we have to add the water. Our Greek prefix is hexa. Hexa means 6, and hydrate is the H2O. Now that we know how to name and write hydrates, the final thing we're going to look at is how to calculate a percentage. The question here is asking, what percentage of the following hydrate is water? We are given the hydrate CuCl2 star 5H2O. Remember, a hydrate includes two things, the anhydrous salt and the water. The question is asking, what percentage of this entire hydrate is water? If you remember from the percent composition video, the first step is we need to figure out what is the molar mass of the compound. All right, let's do that now. We have copper, and copper has a atomic mass of 63.55. Since there's only one, we're going to multiply by 1 and still get 63.55. Chlorine's next. Chlorine has an atomic mass of 35.45. Since we have 2 chlorines, we're going to multiply that by 2, giving us an atomic mass of 70.9. The final part is the water. Now here is a simple, easy way to do the water part. We can lump the water together since we remember water has an atomic mass of 18.02. By remembering this molar mass for water, it will make a lot of our calculations for hydrates go a lot faster and simpler. All right, since we know the molar mass of water is 18.02, let's multiply that by how many waters we have. Our formula says that I have 5 of them, and therefore I'm going to multiply that by 5. If we take 18.02 and multiply that by 5, our total molar mass for the water part is going to be 90.1. If we add all of these values together, our total molar mass for our entire hydrate is going to be 224.55 grams per mole. That includes the anhydrous, salt, and the water. Now the second step is to put the value that we're interested on top over the entire molar mass, which we just found out to be 224.55 grams per mole. Now let's ask ourselves, what part of the hydrate are we interested in? Well, what does the question ask? What percentage of the following hydrate is water? We are interested in the water part. That is the 90.1, and therefore 90.1 is what goes on top. By dividing those two numbers together, we get our fraction of water. It is approximately 0.401. The final step is to just take that answer and multiply by 100 to get a percent. In this case, it's 40.1%. That means that out of that entire hydrate, 40.1% of it is water. This concludes the video on how to calculate and define hydrates.